All right. 2015, day 25. Merry Christmas. Yeah, it's day 25, so it's Christmas. Santa is booting up his weather machine. Looks like you might get a white Christmas after all. Oh, I guess on day one there was a question as to whether or not it was going to be a white Christmas. Oh, that's right. We're fixing his weather machine's snow function. It's powered by stars, and we need 50 stars to power the weather machine. So we're getting close. We have 48. The weather machine beeps on the console. The machine is a copy protection message asking you to enter the code from the instruction manual. What is this? Oh, early video game copy protection. Yeah. Apparently it refuses to run unless you give it that code. No problem. You just look up the code and ho ho ho, Santa ponders aloud. I can't seem to find the manual. You look up the support number for the manufacturer and give them a call. That 49th star wasn't going to earn itself, right? Oh, that machine's quite old. They tell you that model went out of support 6 minutes ago, and we just finished shredding all the manuals. I bet you we can find the code generation algorithm. All right, so we have to just generate a code based on the whatever algorithm. Codes are printed on an infinite sheet of paper. Starting in the top left corner, the codes are filled in by a diagonal, starting with the first row with an empty first box. The codes are filled in diagonally up and to the right. This process repeats until the infinite paper is covered, of course. So the first few codes are filled in this order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I think I understand. For example, the 12th code would be written to row 4, column 2. The 15th code would be written to row 1, column 5. Right. The voice on the other end of the phone continues with how the codes are actually generated. The first code is this. Oh, November the 25th. After that, each code is generated by taking the previous one, multiplying it by this value, and then keep the remainder from dividing that value by that. Oh! So we're doing multiplication with a mod. Right. Okay. I remember that there's a shortcut for that, similar to the way you can shortcut multiplication with repeated addition. Right. So to find the second code, which ends up row 2, column 1, start with blah, 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 blah. Oh, says the voice. It looks like we missed a scrap from one of the manuals. Let me read it to you. You write down his numbers. Okay, so we can use this to check our values. Now remember, that's not even the first few numbers. For example, you're missing the one at 7, 1, which would be down here, which would become before 6, 2. Right, so because we're going diagonal, this one, then this one, then this one, then this one, right? Oh, it's time for lunch. Okay. Let's get our puzzle input. It's 1 line long. Enter the code at row 2978, column 3083. Yeah. All right, first let's see if we can figure out how to generate these numbers. And that'll give us the power, right? Because this is going to be offset by this amount. So we start with this number and then we add this. So this is going to be this number, 252533 to the 1. This is squared, this is cubed to the 4th, to the 5th, to the 6th power. But then we get to mod it this way. All right, so we need to generate these numbers. And these numbers look, at least the first row looks like just sum, right? There's 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so on. So we should be able to generate the first row. And then the second row, we should be able to figure out based on the first row, and so on. Because this is 1, 2, 4, 7, 11, right? So we just need to add the sum, and then we should be able to figure it out, is what I'm saying. So let's see if we can do that. NVim mod. And now day 25. right? Day 25. Let's see if I can do this without making any mistakes this time. This is a 5. That's a 5. And then day 25. And then we edit this. 2015, day 25. And then see if this works. Run. Good. Okay, I did it without any mistakes. Let's see. Now what we can do is just print out the first row. Let's just start with that because that's just the sum value. So let's do this. We've got 1 through 6 and 1 through 6. So let's just do 1 through 6. For n in, let's do I in 1 dot dot 6. And all we're doing is going to say print bang. And the calculation is I times I plus 1, see, n. I'm just a mathematician at heart, divided by 2. And then say println. And that should print out that first row. 1, 3, 6, 10, 15. I didn't put spaces. Let's do that. And now we can see it. 1, 3, 6, 10, 15. 21. All right, because I didn't do equals here. Okay. So now the second row, we should be able to print now. Okay, this is the column. Let's do column, and then we can say for row in 1 dot dot equals 6. And we should be able to determine. Oh, we want to do it the other way around, right? You always loop by column first, by row first, then by column. That's the rule. So this is going to be col plus 1 divided by 2, and that's just going to give us the same sequence each time. Ooh, println needs to be there. Right. So now we just need to shift this up by some amount, and based on a row. And actually, what we can do is create a little row call calculator here. Fun num at RC, and these are U sizes, right? I guess it doesn't matter. We can just use, and these are all, yeah, unsigned. So let's just do U64s for everything. Row call, and we should be able to figure it out. So it's going to be complicated. We're adding, so here we have row 2, so we're adding 1, and row 3 we're adding 2. So it's basically this offset by this, because here's we're adding 3, here's we're adding 4, here we're adding 5. Right, so if we're in column 1, we add the row minus 1. Let's see if we can at least get that one correct. So our base value, that base is equal to col times col plus 1 divided by 2. And then we can say return base plus row minus 1. And for the first row, that'll be 0. Oh. And that all I want to do is print that out here. Num at RC row call. Let's see if we get that first column correct. 1, 2, 3, 4, 5, 6. That's wrong. Right? It should be, oh, it's got to, yeah. Oh, it's plus 1 off of this. So base 2 is going to be, sorry. Here we're adding 1. Here we got 1, we're adding 2. Okay, so we just need this value here and then base it off of that. Okay, we can do that. Right, so we have this value here based on the column, but then we want to get the row to also have that same. Can we do it that way? Row times row plus 1 divided by 2 minus 1. Let's see what that gives us. 1, 3, 6, 10, 15, 21, and we want to subtract 1. Oh, we did. That's interesting. This number is right. 5, 8, 12, 17, 23. That column's correct. And this one's off. Okay. So that's not the calculation. Let's see. Yeah, so this is adding 1. It's just adding 1 to this value. So what if we factor in the row here? That might do it. If I say col plus row, and then col plus row plus 1, it can't be that simple, right? Oops. You just throw it in as a single calculator here. And I forgot that. No. But we're close. Not really. I think we need to shift it down by 1, right? That's our first problem, is we need to shift it down, and then these. Yeah, let's try shifting it down 1. Col plus row minus 1. And then col plus row. Right? Because this is going to be 1 and 1. We want that to be 2. And then we're dividing by 2 each time, but I think we need to divide by 2 minus 2 minus row plus 1. Right? Can't be 2 minus row, because 2 minus row would be 1 for the first row, and we only at least divide by 2. And then we panicked. Subtract with overflow. Maybe we have to say it the other way around. 2 plus 1. So 3 minus row. Attempt to divide by 0. Oh, we can't do that. What if we just divide by 2? Let's see what that looks like. Yeah. And if we so this needs to be 2, this needs to be 4, this needs to be 7. If we subtract, and this is row 2. Let's actually print that out. Row. Yeah. So if we subtract 6 from this, oh, that's not enough, right? It should be 6. It should be 5. Yeah, if I subtract row, just like that, 1, 3, 6, 10, 15, and it should be 2. Oh, I got this wrong. I messed up here. This should be row here. Print, bang, row. Like that. Yeah, that's better. And this is 4 and it should be 5. This is 1 and it should be 2. This is 8 and it should be 9. 13 should be 14. Yeah, I think we're there. We just add 1 to the result. 1 plus this. Is that it? 2, 5, 9, 14, 20, 27, 4, 8, 13, 19, 26, 34. Well, we don't know the last two. But I think the fact that we've got these means we're there in terms of the power that we need. So we should be able to just now say, should we parse the input, or should we just, because these are the values we need to parse out. I could just hard code them. Get input, get commit -m 2015 day 25 input. I'm just going to hard code them. So here, row equals this, let row. Let calling equals that. Oh, I have it backwards with the equal sign. There we go. And now we don't have to do this, and we can just do this. Println. And didn't like that because I put a column. Okay, so now we have what we think is the correct value in the array. Now we just need to raise this by that value, which is an enormous number. But the fact that we get to mod it each time makes it simpler. So what I'm going to do is I'll just create a little function here, which is called mod power mod. And we'll give it the two values. And then what we can do is print these out just to make sure we get it right. Power mod, and these we're doing U64s, so we just need the base, which is U64, and the exponent, which is U64, and a mod. Can't call it mod. What are we going to call it? We'll just spell the whole thing out, and this returns a U64. So now we basically just need to create a loop which will multiply base. Basically, we're going to square the base each time through the loop while there's still an exponent left, and add it into the result if the exponent has the lower bit set. Right. This is similar to the way you multiply two numbers by adding, however, using the just the bits that are actually set to do the additions, which reduces an O of n problem to an O of log n problem, which is huge, especially for numbers like we're seeing here, right? We have, what is this? 18 million. I don't want to multiply 18 million times. But we can multiply by log of that, and that'll go very, very fast. So we have a result. We're going to start off with the 1, because we're multiplying. Multiplicative identity is 1. We want to make sure that our current base equals base modulus. Just make sure that it's within within bounds, and then we say while x is greater than 0. And then we're going to check the lower bit of exp. If exp and 1 equals 1, then we're going to add to our result. We're going to multiply our result and mod by the modulus. Result times base mod modulus. And then after we've done that, we shift the x down by 1, and we square the base. Times base mod modulus. And that's all we need to do for that. And then we got the result. So this is a very straightforward kind of squaring, but keeping it within a certain value, certain range. And the fact that we're just doing it for each bit in exp, that means we have a maximum of 64 to go 64 multiplications here, and a maximum of 64 multiplications here. So it'll be very, very fast. We should be able to then we can put our loop back in here for row in 1 dot dot equals 6, for col in 1 dot dot equals 6. And these numbers are all 3, 6, 7, 8 digits. So we should be able to format it nicely, right? Let's print the row. Bang. Row colon space. And we can say print bang. Actually put the space before. And this is just going to be power mod of, and the base where's the base? First code is this, so we're going to have to add that in. Yeah, so that's the base. Copy, paste. The exponent is going to be the value that we got, which is self num at rc row call, and the mod is this value here. And then we need a println, like that. And oh, that's right, I wanted to have this, so this was 8 colon 8. Is that the way it works? It doesn't like this. Oh, if x and 1 equals 1. Oh, can't assign to this. Let's make that mutable. Okay. Oh, right. I got to add in. Yeah, I was just looking at the values. That's wrong. Oh, interesting. So our first value has to be this. And right now we're seeing this value here, which makes sense, but now we have to subtract that off. Does that mean we actually want to go 0 here? Subtract with overflow, right? So line 11. This is here, where we're going 0 plus 0 minus 1, which isn't going to work. Right, this is the power of 1. Okay, so let's undo that. Let's go back here, but then we want to start here. Maybe we want to set power mod and then just say minus 1 here, right? And then we want to add this value in. No. Oh, do we start? Do we start with this value as our? Oh, no, not add it. We want to multiply it in, right? And then mod the result. So let's do that. So we do this, power mod, right? Because we're multiplying. We start with that number. That means we have to multiply with that number. Actually, that's what we want to do here. Is put this number here. That's the way to do it. Okay. Yes. Okay, yes. These are all the correct numbers. And that means we can return this result here, which is power mod of 252.533 self num at rc. Like that. And I'm subtracting 1 here. You think I'd be able to do that up above, right? And then this number. And here's our row call. And so this is our answer. Is it right? Hey, look at that. We got 1 gold star. We're at 49 and then continue to part 2. And like I said, part 2 is just going to be, we need 50 stars. 1 star is available. You check your fuel tank. Sure enough, a lone star sits at the bottom, awaiting its friends. Looks like you need to provide 49 yourself. You have enough stars to start the weather machine. So before I click that, I want to just look at the calendar. This is what the calendar looks like now with 49 stars. And then once I click starting the weather machine, and now we have snow. Snow begins to fall. Congratulations, you've finished every puzzle in Advent of Code 2015. I hope you had as much fun solving them as I had making them for you. Yes, I had a lot of fun solving them. And now if we look here on the calendar, we have both stars and we have a little Santa sleigh. Yeah, so I've done these two. I almost feel like, well, we're on a roll. We should start with 2016. Before I do, though, this is kind of a generally useful function. Especially if I pass in like start U53, U64, and then you just put start here, and then pass in that value, which is 2015 1125. That should give us the same answer, right? Yeah, those are the same numbers. So now we can make a generally, this should also be start modulus. I wonder if we could just make this a general purpose function, right? We just move it into the library. Make sure this still works. And into a library function. So I can say split and then edit source magic RS. And we'll just move it there. It's a power mod function. And that means we also need to add it to the lib. Mod magic abuse star. And then up here, all we do is say use AOC lib mathemagic power mod. And then that should all still build. And of course it doesn't. It's a private module. Oops. What did I do wrong? Yeah, it is. But I also had mod combo. Oh, I don't need to specify the submodule. Right. I just say power mod. There we go. And then part 2 is ta-da. And let's get rid of these prints. Should we write a parser since we didn't for this? Okay. Let me just double check. I didn't break it. 25 G650453. Yep. Good. So this was the only tricky part that took me a while to figure out, and I got it, went down a couple of wrong alleys there. That wasn't too bad. Git status, git add source lib and source math the magic. Git commit dash m a power mod function. I wonder if we should make it. Ooh, what did I do wrong? There are code style issues. It doesn't like this. Oh, yeah, okay. Fair enough. I can do that. This was complaining about the blank line at the beginning and a blank line at the end, apparently. Okay. Let's try again. And then we just have git add source, git commit dash m 2015 day 25. All done. All right. The only other thing, right, if we want to get a little fancy about it, maybe we just pass in a generic type here for U64. What would that take? Right, because every operator needs to be able to be done. Right? If I just said make these all T's and every U64 becomes a T, this is going to complain that there's no guarantee that we can do this operation with any generic t. So we're going to have to make like a giant where clause, right? Cannot mod t by t. So this is the first error. So we could just say where t, and then we have to be able to do a mod. And I think that's rem. Oh yeah, it says it right here, standard ops rem. Right, but we also need all the other ones. There's rem assign, right? Plus, right? Standard ops rem assign, and then this partial ord, and that's going to be tricky because you have to actually specify the type, I guess. Let's see what this does. Oh yeah, in comparison, right? There's the partial ord. Oh. Yeah, I don't know if this is worth it. So this is a type t and this is an integer. So what we'd have to actually do here for this is just say let 0 equals 0 try into, if we specify that it's of type t, unwrap, and then this could be 0 here. And we have to do the same thing for 1. Convert from integers not implemented. Mousex says, I think numeric types have stuff like t::1 and t::0. Oh, okay. So is there a way to specify a numeric type? Because I was thinking here, to get this part to work would be the adding a from. And then we have to say what this is, what type this is, right? Because try from needs a type like that. And I think that means I have to make this an I32. Oh, and then we need debug because unwrap requires it to be able to debug out. Mousex says code actions are stuff that Rust Analyzer sends to NeoVim, and then the LSP plugin can list those actions and apply the recommendation edit. Oh, the recommended edits. That would be sweet. That would be something to explore. Maybe we take a look at that instead of doing all this crazy stuff. I'm just gonna see because now I'm down this. I'm down this rabbit hole. Oh, debug. I meant debug, right? Not display. And it's this whole wacky thing, right? So it's not just. Oh. Can I copy that whole thing? Yeah, and then we got this wacky character in there. Will that work? Expected identifier. Oh. This is like a separate thing. Yeah, okay. And then we have standard compare partial ord. Actually, we're getting close, aren't we? Should I keep going? Bitwise and. Maybe instead of doing a bitwise and, we can just do mod. There. Mod 2. Oh, we have to do a 2. Right? Let 2. Oh, we have to do 1 as well. The question is, Mousex, how do I specify that it's a numeric type? There might be a way to do that, and then I can just use like : 1 : 0, like you said. So if we do 0, 1, and 2, so this becomes 2 is equal to 1, and then this gets shifted by 1. Oh, and then we have to do comparison. What is this? Oh, right. This needs an output equals t. Oops. There. So now, okay, we're getting closer. So now we just need this mul plus that. Oh, and then we need the output for that as well. comma goes there. And now we're in, and then sure assign. Okay. Let's do this here. Plus. And this probably needs an output. No comma there. Oh, there's no output on that. And now we have this. This needs copy. Okay. There, that's all we needed to do. Super easy. Does it run? Yeah, and it comes out with the right answer. Okay. So now we can use any type, or any numeric type that can be converted from i32. That's pretty wacky. All right, let's do that. Get diff. Yeah, so the only thing I had to do is change these, the hard-coded things here. Okay. Git add. I wish we could do, you could do like optional arguments in Rust, because this would be nice to set this to 1 if not specified. EpicBlog says, now that's a trait bound. Yeah. Every single operation here needed a bound on it. But fortunately, the Rust compiler was telling me exactly which ones to add. So that made things simple. Source git commit status git commit -m make. This is probably the most useless change I made, because U64 is probably fine for everything. Make the arguments for PowerMod generic.